Hello everyone, my name is Karan Gaikwad. Welcome to the week 7 project for advanced structural mechanics. The topic for this week's project is finding out the deformed areas and volumes for the composite body. So the composite body that I've came up with is a combination of a hemisphere and two cylinders, which basically combines together to form a table lamp. The vector field that I've used can be imagined as the expansion of the composite body in the transverse direction that is perpendicular to the axis of this body. So this is the deformation map for the composite body, which is basically I've just added Z1, Z2, and Z3 to the displacement field that we have used in the previous projects. So this is the deformation gradient, which is basically obtained by differentiating x1 with respect to z1, x2 with respect to z2, and x3 with respect to z3. Coming to the parameterization, these are the parameterizations that I've used to come up with the composite body. And these are the tangent vectors, which are basically obtained by differentiating z1, z2, and z3 with respect to r, phi, and theta for the hemisphere, and small r, theta, and z for the cylinders over here. So coming to the MATLAB output, this is the MATLAB output that I've obtained after running the code, which is similar to the output obtained from the last week's project. The only difference here is that it gives us the undeformed and deformed areas for all the parts of the body. So as you can see, these are the areas for every surface that I've defined. And this is the volume for all the three parts. So in this project, we will uh, cross-check and verify the area and volume for this particular part of my body, which is basically the base of this cylinder. So coming to the verification of the area for this circle right here. So this is the parameterization for the circle, and the undeformed area comes out to be pi r square. And we substitute the coordinates for the we substitute z1, z2, and z3 for the deformed uh, surface into the map of the composite body, and then obtain the area Jacobian by differentiating x dx with respect to r and then theta, and then we obtain the area Jacobian, which is basically the cross product of these. And then we integrate the area Jacobian with respect to the limits of r and theta, which is 0 to 2r and 0 to 2 pi for the cylinder, which come out to be 3.395. As you can see, it's pretty close to 3.3928. So we are good over here. Coming to the volume, the volume is calculated for the similar part here as well. So this is the parameterization for that particular part of my body. And the undeformed volume comes out to be pi r square h. The h here is 3, that is the height of this object. Coming to the parameterization of the deformed body. So this is the parameterization obtained for the deformed body, and then we just substitute the parameterization for the undeformed body into the map, and then obtain the parameterization for this thing. And then for the volume Jacobian, we take the cross product of the derivative with respect to r and theta for the first two, and then take its dot product. So basically it's a triple product to obtain the volume Jacobian. So this is the volume Jacobian that I've obtained, which came out to be pretty complex. And this is the deformed volume I obtained after integrating the volume Jacobian with respect to the limits for capital for small r, theta, and z. So this is the value that I came up with, 10.9647, which is a bit skewed off as compared to the MATLAB output, but I guess it's within the acceptable limits. So I tried this alternative approach, like I've imagined the deformed surface as an ellipse and tried to calculate the deformed area through the formulas for the ellipse. So I've tried something different for this part actually for verification purposes. I don't know if it's correct, but I've tried this as well. So coming to the actual code, we can try and run the code right now. It takes a bit longer to run the code. Yeah, so this is the code and it runs successfully. Thank you so much for watching this video. Have a good one.